This is an aging concrete arch hydroelectric facility located in the mountainous topography of southern France, designated in engineering literature simply as Dam EDF. For decades, infrastructure managers have relied on rigorous structural health monitoring to ensure the integrity of dams like this one. The goal is to detect early signs of material degradation before they escalate into catastrophic failure. The challenge is that these massive structures are constantly moving. A concrete dam undergoes cyclical thermal expansion and contraction as seasons change, creating a baseline of ambient noise that masks actual structural shifts. Compounding that thermal noise are the massive, fluctuating hydrostatic loads. As the reservoir fills and drains, millions of tons of water pressure push against the concrete, forcing the arch to flex. To completely cut through this environmental noise, the International Commission on Large Dams, or ICOLD, organized a massive benchmark workshop. Theme A of the 2022 workshop tasked engineers from around the world with building a predictive behavior model for Dam EDF. This scatterplot shows the calibration data set, 12 years of raw radial displacement recorded by two pendulums inside the dam. The task was to extend a mathematically rigorous trend line from this dense data into the blank horizon of the future. Participants had to deliver two specific forecasts. First, a short-term 6-month prediction to test immediate accuracy. Second, a long-term 4.5-year extrapolation to test the model's durability over time. Prediction alone is insufficient for infrastructure management. Participants also had to define specific safety warning thresholds based on their models to establish exactly when a measured displacement should trigger an alarm. Retroactively fitting a curve to past data is a straightforward statistical exercise. The true test of a structural safety model is its capacity to isolate the physical truth from statistical noise and accurately forecast out-of-distribution future events. This topographic map outlines the geometry of the structure. It is a 45-meter-tall, double-curvature concrete arch. Because of the specific shape of the river valley it occupies, the arch contains a distinct structural asymmetry where it ties into the left and right banks. This cross-section shows the pendulums in the central block tracking radial displacement. The benchmark requires predictions for two specific readings. CB2 tracks the concrete dam body, while CB3 extends deeper to measure the foundation rock beneath the structure. Dam EDF sits atop a glacial threshold. When the reservoir drops below 196 meters, the water recedes completely into a lower lake. This exposes the concrete's upstream face to ambient air, radically altering its thermal load parameters. Below the surface, the mechanical properties of the rock mass present another complication. The foundation exhibits viscous effects, meaning the rock reacts to loads with a delayed response compared to the immediate flexing of the concrete arch above it. These physical quirks, the asymmetric geometry, the glacial threshold, and the viscous rock, turn a standard data problem into a highly site-specific engineering challenge. This line graph tracks the reservoir water levels from 1995 to 2018, mapping the primary structural driver recorded in the calibration dataset. This scatter plot maps the corresponding air temperatures, showing the strict seasonal cycles that act as the secondary environmental driver. Falling water relieves pressure, causing the dam to lean upstream. Conversely, summer heat expands concrete, pushing the structure downstream. A severe water decrease, perfectly counteracted by rising temperatures, creates zero net displacement despite massive environmental load shifts. Participants also had to wrangle raw data. The provided time series were measured at different frequencies, requiring careful alignment before any algorithm could process them. Raw displacement data alone is functionally useless without the ability to mathematically isolate, weigh, and calculate the distinct physical loads driving that movement. Faced with these variables, participants had to choose between two primary modeling pathways: data-driven models or deterministic numerical models. Data-driven models treat the dam as a black box, bypassing physical laws. They use statistical correlations to map environmental inputs directly to displacement outputs. Participants deployed various algorithms, from classical hydrostatic seasonal time models to advanced machine learning frameworks. Training these algorithms required clever feature engineering. Some teams inputted 54-day moving averages to account for concrete's thermal inertia, while others mathematically capped the input water level at 195 meters to reflect the glacial threshold. The primary advantage of the machine learning approach is its unparalleled mathematical accuracy. When operating within known environmental conditions, these algorithms predict displacement with exceptional precision. The second pathway uses simulated physical laws. This rendering shows the 3D tetrahedral foundation mesh used in finite element modeling. Its core advantage is physical interpretability, allowing engineers to visualize actual internal compressive stresses within the concrete itself. However, models relying purely on data carry a specific risk: overfitting. Because they lack an understanding of physical limits, they can output wildly inaccurate predictions when exposed to out-of-distribution events they haven't seen in training. Finite element models, conversely, demand complex, iterative calibration. Engineers must constantly adjust assumptions about material properties, like the rock modulus of the foundation, just to get the simulation to match the baseline sensor data. It is a deliberate trade-off. Machine learning offers deep statistical precision, while finite element modeling offers the safety and constraint of immutable physical boundaries. Regardless of the methodology chosen, every model required a calibration phase. Participants actively tuned their parameters against the 2000 to 2012 baseline data to minimize the residual error between their predictions and the actual pendulum readings. For the data-driven teams, this meant running thousands of cross-validation loops, pseudo-randomly testing different combinations of inputs to find the most robust mathematical fit. For finite element teams, calibration meant iteratively lowering the foundation rock modulus until the digital model accurately replicated the delayed physical response of the CB3 pendulum. But high-accuracy forecasting is only half the engineering task. A prediction line is useless to an infrastructure manager unless the model also defines actionable warning levels around it. Mathematically, a warning threshold features upper and lower boundary envelopes, flanking the predicted curve. If sensor data crosses these lines, the behavior is anomalous. Engineers typically set these boundaries at 2 to 3 times the standard deviation of the calibration error. These mathematical thresholds form the critical buffer between acceptable statistical noise and the trigger for an emergency structural intervention. This heat map ranks the forecasting accuracy across the different methodologies for both the short-term Case B and long-term Case C timeframes. The results show that no single participant or model type universally dominated across all variables. Standard industry practice involves recalibrating behavior models annually. Demanding a 4.5-year long-term prediction was an intentional, extreme stress test, reflected in the wider spread of red and orange errors in the Case C columns. Hidden within that long-term forecast window was a major out-of-distribution anomaly, an extraordinary reservoir drawdown event that pushed environmental loads beyond anything seen in the calibration data. This sudden, massive drop in hydrostatic load severely tested the extrapolation limits of every calibrated model, testing how they handle unprecedented physical strain. Models relying purely on statistical correlations struggled to maintain accuracy during this event. Without accounting for the physical reality of the glacial threshold exposing the concrete face to the air, the algorithms lacked the context to correctly interpret this sudden shift in thermal behavior. While pure machine learning models ultimately provided the highest overall displacement accuracy across the benchmark, the results proved they require intense feature engineering and manual constraints to prevent dangerous overfitting. Advanced predictive algorithms cannot be deployed blindly as black boxes. Securing critical infrastructure requires fusing high-precision data science with deep site-specific physical engineering judgment.